Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss the exponential and trigonometric functions when the arguments are complex numbers. In this topic, we will deduce Euler's formula. We will then make some observations about Euler's formula. We will then see a geometric interpretation of how you can have a complex valued function of a real variable. We will then determine the result when e is raised to a complex power. We will verify that this is reasonably correct and make some observations, including deducing formulas for cosine of z and sine of z when z is complex. To begin, recall that the magnitude of z phase theta is equal to the magnitude of z cosine theta plus the magnitude of z sine theta j. Thus, 1 phase theta is equal to cos theta plus sine theta j. Now, in calculus, you either have seen or will see that the exponential and trigonometric functions can be written as Taylor series. Here we see that e to the x can be calculated as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. This can be written compactly using summation notation as follows. Similarly, you will see that cosine of x can be written as a Taylor series, which has this compact representation, and also sine of x has this Taylor series, which can also be written in this notation. Notice that cosine is an even function. That is, cosine of negative x is equal to cos of x, and cosine of x, the Taylor series, only contains even polynomial terms. However, sine of x is an odd function, sine of negative x is negative sine of x, and sine of x's Taylor series only contains odd powers of x. Now, let us substitute x with j theta. In this case, we see that e to the j theta is equal to 1 plus j theta all squared over 2 factorial plus j theta cubed over 3 factorial, and so on. But remember that the power of a product is the product of the powers. Therefore, we can take out the j and rewrite this series as follows. But wait a second. J squared is negative 1. J cubed is negative j. J to the fourth is 1 again, and j to the fifth is j, and so on and so forth. Therefore, this series can be simplified as follows. So notice that every second term is real, and the other terms are all complex or imaginary. Let us collect the real and imaginary terms. So now we see that e to the j theta is equal to one real series plus another real series times j. Let's take a look at this sum of two series, one real and one imaginary. Now, does that first series not look like the series for the cosine function when the argument is theta? And does that second series not look like the series for sine when the argument is theta? Thus, is it not fair to say that e to the j theta is e cosine of theta plus sine of theta j? In fact, it is, and this is actually called Euler's formula. Thus, can we not write the magnitude of z phase theta as the magnitude of z e to the j theta? In fact, yes, we can. These two are equivalent statements, and some engineering disciplines will use the first. They will use magnitude of z phase theta, while other disciplines within engineering prefer to use the other magnitude of z e to the j theta. However, they are both equivalent, and you should get used to both. Now, some observations. The magnitude of e to the j theta is 1 for all theta. Proof. As e to the j theta is equal to cosine theta plus sine theta j, it follows that its magnitude is just the magnitude of that expression. But the magnitude of that expression is the square root of cos theta all squared plus sine theta squared. But that's equal to the square root of 1, which is 1, and we are finished. Before we can consider the geometric interpretation of the complex exponential, first we must review plotting in general. In secondary school, when you plotted cos of theta, it was up to you to plot the value of cos of theta for all values of theta on the abscissa. In this case, we've plotted cos of theta for all values of theta between negative 4 pi and 4 pi. If you wanted to determine what cos of 1 was, you could locate 1 on the abscissa and then determine what the value of the function is at that point by following that point up or down to the function. Now, if we are going to plot in 3 dimensions, we must unfortunately be plotting still in a plane. So we need some sort of projection. So first of all, if we are plotting a 3-dimensional value x, y, and z, we use the right-hand rule to determine the directions of the axes. When we plot a point in 3 dimensions, it's absolutely necessary to give a hint as to where that point is relative to the axes. For example, in this case, the point in question is 1, 2.3, negative 1.7. However, that same point may actually be representing the value negative 3.8, negative 1, negative 5. Thus, some sort of highlight or guidance as to where the point is relative to the axes is essential. Again, this is the result of plotting 3 space onto a plane. When we are plotting a complex valued function f of a real variable, we're going to use all 3 axes. The first axis, x, is the independent variable. In this case, it will be theta. The second axis, y, will be the real component, and of course, the positive direction of the real component goes to the right. The last axis, z, will be used to display the imaginary component of the function, and again, the positive imaginary axis is pointing up. Suppose we want to plot a function f on the interval from negative 4 pi up to pi. We're actually going to do this, first for cosine of theta, and then for e to the theta j. First, we note that cosine of negative 4 pi is equal to 1. We're going to emphasize that this green dot is the result of evaluating the function at negative 4 pi by using an arrow. Now, we won't be able to do this for every single value, but we'll try to do it for a reasonable number of them. Next, at the point negative 3.5 pi, we see that cosine of that value is 0. And thus, we plot that point there at 0. Next, we note that cosine of negative 3 pi is negative 1. And so now we plot the point negative 1 relative to negative 3 pi on the first axis. Continuing this for all values of theta between negative 4 pi and 4 pi, we see a plot of cosine of theta as seen here. You will note that the 0 component is always 0, and thus the image or the value of cosine of theta always lies in the xy plane. Next, let's plot e to the theta j. This, however, is a complex valued function. So while we note that e to the negative 4 pi j is equal to 1, we note immediately next that e to the negative 3.5 pi j is equal to j. Now, to emphasize that this is an imaginary number, we're going to highlight the magnitude or the value of the imaginary component by using green for numbers where the imaginary component is close to 0, magenta for those that are most positive in the imaginary component, and darker colors for those that are more negative. Next, we see that e to the negative 3 pi j is equal to negative 1, and thus this point is highlighted with green again. E to the negative 2.5 pi j is negative j, and so we plot that point relative to negative 2.5 pi directly beneath it. Next, we see that e to the negative 2 pi j is equal to 1 again. Well, what we can continue to do is carry this on with other values, and we note that there seems to be a cycle here, and indeed there is. For if we were to plot e to the theta j for more values of theta, this would reveal a corkscrew motion. There is no such periodic behavior for e to the x when x is a real value. However, e to the theta j is going to corkscrew through the complex plane for all values of theta, going from negative infinity to positive infinity. Now, our next question. If z is equal to alpha plus beta j, what is e to the z? Solution. Well, from secondary school, you already know that e to the x plus y is equal to e to the x times e to the y. Thus, e to the alpha plus beta j is equal to e to the alpha times e to the beta j. And that's equal to e to the alpha times cosine of beta plus sine of beta j. As an example, let's try this out. Let z is equal to 0.09 minus 0.3j, and let us calculate e to the z using the exact formula, and then we will approximate e to the z using a truncated Taylor series. Now, starting with the formula, e to the z is equal to e to the 0.09 times cosine of negative 0.3 plus sine of negative 0.3 times j. Well, we can calculate each of those and expand that out to get that the result is approximately 1.0453 minus 0.32335 j. Now, let's approximate e to the z using a fifth order Taylor series approximation. That is, we will sum up the Taylor series up until the fifth power. So first of all, let us first calculate the powers of 0.909 minus 0.3j first raised to the power 0, then 1, then 2, then 3, then 4, then 5. Now we can divide each of those terms by the corresponding factorial. Now, if we were to add all of these up together, we would get that e to the 0.09 minus 0.3j is approximately equal to this complex number. Let's compare the two results. Well, taking a look at the formula and the fifth order Taylor series approximation, we see that it is correct to at least 5 decimal places or 5 significant digits in each the real and imaginary components. Theorem: the conjugate of e to the z is equal to e to the conjugate of z. Proof: if z is equal to alpha plus beta j, then the conjugate of e to the z is the conjugate of e to the alpha plus beta j. But e to the alpha plus beta j is e to the alpha times e to the beta j. And we know that the conjugate of a product is the product of the conjugates. Also, e to the alpha is real, so the conjugate of a real number is itself, and e to the beta j is cosine of beta plus sine of beta times j. But the conjugate of the second term in that product is just cosine of beta minus sine of beta times j. Now, recalling that cosine of negative beta is equal to cosine of beta, and negative sine of beta is positive sine of negative beta, we can rewrite that expression as follows. But wait a second. Now we have simply written this as e to the alpha times e to the negative beta j, which is equal to e to the alpha minus beta j, which is e to the conjugate of z, or e to the z star. Theorem: the conjugate of e to the theta j is just e to the negative theta j. Proof: well, actually, this is a trivial consequence of the previous theorem. Here's a nice little result. E to the pi j plus 1 is equal to 0. To prove this, e to the pi j plus 1 is cosine of pi plus sine of pi times j, all plus 1. But wait a second. Cosine of pi is negative 1 and sine of pi is 0. So we're left with negative 1 plus 1, which does equal 0. Now, quick question. What is cos of z and sine of z for a complex argument? Well, we know that for a real theta, e to the theta j is cos of theta plus sine of theta times j. Let us posit that e to the z j is equal to cos of z plus sine of z times j, even if z is now a complex number. In that case, we have e to the zj is cos z plus sine z of j. E to the negative zj is cos z minus sine of j. Summing up both sides of the equation, we get that the sum of the exponentials is 2 times cos of z, and thus we can calculate cosine of z as e to the zj plus e to the negative zj all over 2. Similarly, you can show that sine of z is e to the zj minus e to the negative zj all over 2j. To summarize, in this topic we described how to calculate the exponential function when the argument is complex. We first deduced Euler's formula that e to the j theta is equal to cosine of theta Here are some references, acknowledgements, the colophon, and a disclaimer. Cheers!